Welcome, guys. So last time we have seen Article 2.4, there is a probability of an event. And we also went over Article 2.3, that was um, permutation and combinations. We saw the difference, we saw plenty of examples. And then after we saw the probability of an event, the probability should not be less than 0 and it should not exceed 1. So probability always lies between 0 and 1. So that's what we saw last time. And then after I told you that rule 2.3, if an experiment can result in any one of capital N different equally likely outcomes, and if exactly small n of these outcomes corresponds to event A, then the probability of the event A, P of A, that is small n divided by capital N. And we solved some examples too. So that was the end of Article 2.4. We are going to solve some examples together with Article 2.5. So first, let me start with Article 2.5. And once we are done with Article 2.5, then after we can solve some examples based on Article 2.4 and 5 simultaneously. So let me start with this one, the Article 2.5, that is nothing but the additive rule. You can see you can see here this additive rule. That means if you have one event A, another event is B, you know that A union B, that means whole part, but you need to consider only the intersection part once. That means A, probability of A plus probability of A means this part, probability of B means this part. That means we are counting this part twice. So just remove once. So probability of A plus probability of B minus probability of A intersection B, that is the A and B. So that is called additive rule. You can see the addition sign over here. And suppose you have two mutually exclusive events. In that case, A intersection B is 0. So in that case, probability of A and B, A union B is nothing but probability of A plus probability of B. Proof is so simple. Let me skip that part. The mutually exclusive event, as I told you, probability of A plus B. In that case, you have one circle over here, another circle is over here, and there is no common part. So that is just as a part of corollary, we can say that if A and B are mutually exclusive, in that case, probability of A union B equal to probability of A plus B. And we can extend the same idea for n number of events. Here we have just two events, A and B, but suppose we have n1, n2, n3, or A1, A2, A3 up to an events. And if they are mutually exclusive, in that case, we can say that n events, A1 to an, mutually exclusive, nothing is common in this A1 to an, all n events. We can write probability of A1 union A2 union union an, that is equal to individual probability of A1, A2, A3 up to an with summation sign. So probability of A1 plus probability of A2 probability of an, that is for mutually exclusive event. And as you know, that's this thing that A1, A2, A3 up to an, that means these are nothing but the partition of your event n, partition of your sample space S. That means in your sample space, some of the portion is occupied by A1, some of the portion is occupied by A2, and so on. Some of the portion is occupied by an. That means if you take the sum of all these A1 plus A2 plus an, you're going to get your partition or your sample space S. So that's why once your sample space S, that's why in the next corollary we can learn in terms of the probability. So if A1, A2, an is a partition of the sample space S, then probability of A1 union A2, that is equal to just same as this one because mutually exclusive, and that is equal to partitions of probability of full space S, sample space S, and that probability must be equal to 1 because that's the maximum probability. So probability of A1, A2, if you count all these probabilities, that probability will go to 1. Same way, suppose you have 3 events. I talk about 2 events, then after we extended the idea for n events. Now, in particular, suppose I'm going to go for 3 events, A, B, and C, or you can say A1, A2, and A3. And suppose they are not mutually exclusive, that means some of the portions are common. In that case, we can say that probability of A1, A union B union C is equal to probability of A plus B plus C minus probability of A union intersection B, probability of A intersection C, probability of B intersection C, plus probability of A intersection B intersection C. We can learn this thing in detail, whatever I explained to you, corollary 2.2, 2.3, and theorem 2.8. All these things I would just like to explain to you using some Venn diagram. But before that, I just want you to read this example. If you read this example, that will give you probably a little bit more idea. So it says that John is going to graduate from an industrial engineering department in a university by the end of this semester. After being interviewed at 2 companies he likes, okay, after being interviewed at 2 companies he likes, he accesses that his probability of getting an offer from company A is 0.8. That means he assumes that he's going to get the job letter or offer letter from company A, that is 0.8, and his probability of getting the job letter from or offer letter from company B is 0.6. If he believes that he might get the job letters, offer letters from both the companies, he will get the jobs or offers from both the companies. What is the probability that he will get at least one of these jobs of 2 companies, at least one of these, either A or B? Because or is there, we need to use union. I told you so many times, union means or, intersection means and. So A union B, probability of A union B, because he has, now look at the assumptions that he might get the first job offer letter from company A or company B, or it could be possible from both companies. That means A union B means events are not mutually exclusive, right? Some common portion is there. He may get the job offer letter from both the companies. That means I cannot exclude this intersection part. So A union B equal to probability of A plus probability of B minus probability of A intersection B. All these probabilities are provided to you. Here is 0.8 for A, 0.6 for B, and common part from both A and B is 0.5, plug the values. So probability of getting job at least from one of these companies, either A or B, is 0.9. So that's how we can go for this one. Second example is like this. We are going to solve this example, but just you read this example and then after I just would like to go for my whiteboard. So what is the probability of getting total of 7 of 11 when a pair of fair dice is tossed? See, what is the probability of getting a total of 7 or 11? So either you want 7 or 11 when a pair of fair dice is tossed. That means you have 2 dice and you want to toss these 2 dice and you want either 7 or 11. So that's what you want to figure it out, right? So how many total ways are there to get 7? Now it could be possible that if you look at the 1 die, so 1 die, how many numbers are there? 1, 2, 3, 4, 5, 6. Second die, 1, 2, 3, 4, 5, 6. If you want 7 by tossing both the dice simultaneously, that means it could be possible that on 1 die you may get, suppose 6, another die 1. So 6, 1 is 1 pair. Then first die 5, another die 2. First die 4, another die 3. First die 3, another die 4. First die 2, another die 5. First die 1, another die 6. So these are different ways. These are different ways that you can get 7 from tossing both the dice simultaneously. So A be the event where 7 occurs, and if I say capital A is the event where 7 occurs, capital B is the event where 11 occurs. Now, how many possibilities are there or outcomes are there to get 11? Suppose I roll 2 dice or 2 dice. That means I'm going to get either 6 on 1 die, 5 on another die, or 5 on 1 die, 6 on another die. These are only 2 possibilities. So 6, 5 and 5, 6 to get 11, right? These are only 2 possibilities. Now, the individually, what will happen? How many total points are there? Sample points that on first die 6 points, second die 6 points. So 6 into 6, n1 times n2 is 36 outcomes. So total outcomes are 36. Total outcomes are 36. Out of these total outcomes, if you want 7 by tossing both dice simultaneously, how many possibilities are there? As I told you that, yes, 6, 1, then 5, 2, 3, 4, 3, 3, 4, like this. So there are total, yes, 6 possibilities. That means probability of getting A, that is 6 divided by 36, because 6 is your small n, 36, that is your capital N, total number of outcomes. And that is just like your previous article, as I told you. That's the reason I just referred to rule number 2.3 before the beginning of this lecture. So that is small n divided by capital N. Small n here is your, you can see over here, small n is nothing but, I think it's written in terms of words, so probably a little hard for you, but you can say small n is 6 and 36 is the total number of sample points, so 6 divided by 36. That is your probability of A. Same way, probability of B. There are only 2 outcomes, 5, 6 and 6, 5 to get 11. So 2 divided by 36, small n divided by capital N, 2 divided by 36 means 1 divided by 18. There's a probability of B. probability of B. Your probability of A is 6 divided by 36. Probability of B is 2 divided by 36. Don't count 1 over 18. Of course, 2 divided by 36 is 1 over 18. But actually, if you write 2 divided by 36, that will make more sense understanding this concept. And then after, if you go for probability of A union B is, now both the events are mutually exclusive. Once you roll both the dice, so you are looking for the probability of getting only 7. Sum is 7 or 11. But there is nothing common. It's not possible simultaneously that you are getting some 7 as well as even together. It's not possible. Absolutely impossible. Either you are going to get 7, 4, and 3, or suppose it is 5 and 6, so it is 11. But both simultaneously will not happen. So that is why both the events are mutually exclusive. That's why I would like to use this rule, probability of A union B equal to probability of A plus probability of B. Probability of A, I figured it out, that is equal to, yes, please, 6 divided by 36. So I would like to write 6 divided by 36 over here, 2 divided by 36. 6 plus 2 is 8 divided by 36. 8 divided by 36, that means you have 2 over 9 is the probability. So the author brought it down over here, just like in a compact form. But I would say that please try to stay with your concept and try to write the big number. That's fine. That doesn't matter. Ultimately, you're going to get the same answer. Same way, the result, this is for probability of getting 7 and this one. Okay. This result could also have been obtained by tossing or counting the total number of points from the event A union B. 8, see, n divided by n, I told you. So 8 divided by 36, that is equal to 2 over 9. Same way, either you can go for individual or you can write total sample points are 36. 6 outcomes you are going to get from event A. 2 outcomes you have, because 11 can be obtained just by 2 ways. 7 can be obtained by 6 ways. 6 plus 2 is 8. My small n is 8. Capital N is 36. So small n divided by capital N, that is 2 over 9. So both the ways, this is actually OR part. Both the ways you're going to get the same answer. Let me switch to the whiteboard so that I can let you know about this corollary 2.2 and theorem 2.8 in a perfect sense. So let me stop sharing this book and let me go for my whiteboard. Whiteboard says something like this. It says that, as I told you, that A1, A2, An are mutually exclusive. In that case, what will happen? Actually, we are corollary 2.2. So it says something like this. This is my sample space. This is my sample space. Out of this sample space, suppose some portion is occupied by A1, some portion is occupied by, suppose, A2, some portion is occupied by A3, some of the portion is occupied by, suppose, A4, and then some of the portion is occupied by A5, like this. Some of the portion is occupied by, suppose, A6, and so on. And say some here, same way you have n number of partitions, see here, like this, like this, like this. It could be anything, right? Like this, and finally an. So you can see here that if you write A1 plus A2 plus A3 and dot, dot, dot up to an, that means you're going to get your sample space S. And that's why if you go for probability of A1, A2, an, so this probability is nothing but individual probability of A1 plus probability of A2 because of the mutually exclusive event A3 and dot, dot, dot plus probability of an, and that is equal to probability of S. But we are looking for the probability of the whole full space, and it has to be equal to 1, right? It should not exceed 1, but it has to be equal to 1. Same way, my theorem 2.8 says that, that is for 3 events. Suppose you have 3 not mutually exclusive events, but suppose you have 1 event over here. This is my event A. Second event is over here. This is my event B. This figure is not given in the book, and that's why probably it is a little hard for you to understand this concept. So please try to pay attention over here towards this Venn diagrams. It will give you a little bit more idea. And we are looking for, look at here. If I'm looking for probability of A union B union C. So probability of A union B union C, that is equal to, oh, sorry, I placed something else. So let me just keep this part so that we are again back on the white screen. Okay. So A union B union C, that is equal to, yes, please. Now probability of A. If I write probability of A, oops, what's wrong with this? Let me, something goes wrong. think I need to stop the whiteboard. If I stop the whiteboard, all the things will be gone. So let me, something is, why this cursor is working. Okay, so let me do one thing, guys. Let me just stop sharing and let me again go back to the whiteboard. Oh, that's good. So we are getting the same picture which we are looking for. That's good. So now probability of A union B union C, that is equal to probability of A plus probability of B plus probability of C. Now, if you take probability of A, that means full A is counted. Full A is counted. Now, if you take probability of B, that means you can see over here, this portion is again counted. This portion is again counted. That means I need to remove this portion. What is this portion? This portion is A intersection B. Agree, guys? So A intersection B. So I need to remove this, the negative of probability of A intersection of B. Let me remove it because it is just counted in the first part. Same way, if I'm looking for probability of B, that means the whole portion, this intersection is gone, whole portion, but this one is counted one time. See, every time this portion is counted. But now intersection B, that means that one time has gone. So probability of B, that is now this part, and probability of B, but it counts this part, and probability of C, it is counting this part also. So again, this portion is counted twice. This intersection portion, this is nothing but B intersection C. So let me remove that part. So minus probability of B intersection C. Same way, suppose you go for probability of C. So probability of C, already it was counted in probability of A. So this portion is counted again one more time, it is A intersection C. So let me remove that part also, probability of A intersection C. But every time, see, whenever you are counting probability of C, that it doesn't count just only this portion A intersection C part. It counts that this common portion also. So common portion is one more time. So I have to remove, I have to add that part, because every time when you remove this A intersection B, that means the whole part has gone. This whole intersection part is gone. If you write B intersection C, again the whole part has gone. This whole part has gone. If you remove this A intersection C, again the whole part is gone. So ultimately, we want to remove this part. We want to remove this part. We want to remove this part. But we want this just one common portion because that was not counted. We want this common portion for A, B, and C. So I'm going to write that is equal to plus A intersection B intersection C. So that's why this formula has been developed, that probability of A union B union C, that is equal to probability of A plus B plus C minus A intersection B minus probability of A B intersection C minus probability of A intersection C plus probability of A union A intersection B intersection C. That's the reason, guys. So now we just went over these two problems, and now again I would like to go for the example based on this one. Example 2.31 in your book. Example number, let me change the color, probably helpful to us. 2 point, let me write it down over here. 2 point, no space. Okay. 2.31. Example 2.31. It says that, please listen to me carefully. If our probabilities are respectively 0.09, 0.15, 0.21, and 0.23. 0.09, 0.15, 0.21, 0.23. That a person purchasing a new automobile will choose the color green, white, red, and blue. Green, white, red, and blue. That means the probability of green, probability of white, probability of red, and probability of green, white, red, and blue. Probability of this is P. Probability of this is P, please. Probability of B. Probability of green is given to you 0.09. Probability of white is given to you 0.15. Probability of red is given to you 0.21. And probability of B is given to you, that is equal to 0.23. I read the example. These are the probabilities that a person purchasing a new automobile will choose the color green, white, red, or blue. What is the probability that a given buyer will purchase a new automobile that comes in one of those colors. Now, guys, one thing is very sure. Suppose I go and I go to buy a car and if I choose, suppose my car color is white, right? My car color is white. That means naturally my car color will not be green or red or blue, right? Same way, suppose I choose my car color is green, it could not be either white or red or blue. Or suppose my car color, I chose suppose blue, that means my car color will not be either green or white or red. That means a mutually exclusive event. So I would say that mutually exclusive event. So if I'm looking for the probability of buying the car, so probability of, I'm sorry, eraser, and let me remove this part and okay. So probability of buying the car, so probability of buying either green or, union means or, white or red or blue, that is equal to probability of green plus white plus probability of red plus RB. And that's it, because it's a mutually exclusive event. So that is equal to, these probabilities are already provided to you. Just take the sum and you are going to get that is equal to 0.68. That is the answer. So probability of getting one of the cars, or probability of getting a new automobile that comes in one of the colors, that is this one, right? So this way you can go for the mutually exclusive events, mutually exclusive probability of the mutually exclusive three events, probability of mutually exclusive three events. Then the last small concept is left out in this article, that is if A and A cap or A dash are complements of each other. Complements means, let me save this file and let's go for the next one. So let me save this one, save in a folder and save it. And let me clear the file. Now, suppose I have my sample space S, and this is my event A. So elements which are not in A, that is called A complement. I told you that some people, they write A dash, some people write A to the power C. Usually we do not write dash. So it's a complement of an event, right? So naturally probability of A plus probability of A complement, that is equal to probability of the full space, and that is equal to 1. So always keep in mind this thing, that is equal to probability of 1. So sometimes it may be possible that suppose you want to find the probability of A, or it is better to find the probability of its complement. It is easier for us to find the probability of a complement. So I can write probability of A like this, or vice versa. So always keep in mind this thing, that probability of A dash equal to 1 minus probability of A, 1 minus probability of A. I can give you one more example based on this one. Again, listen to me. Your example number 232 in the book. So book example 2.32, page number 58. Page 58. Okay, so it says that if the probabilities that an automobile mechanic will service. Now, automobile mechanic servicing either 3 or 5, 4 or 5 or 6 or 7 or 8 vehicles or cars on any given work day, on a work day. Either he can fix 3 cars or 4 cars, depending on how much fixing is required to get it done. So probability is that the automobile mechanic will serve 3, 4, 5, 6, 7 or 8 or more, 8 or more. If some small issues are there, then in that case, in that particular day, he may fix more than 8 cars too. Okay, on given work day. And these probabilities are given, probability of 3, that is 0.12. Probability of 4, that is 0.19. Probability of 5, that is equal to 0.28. Probability of fixing 5 cars a day, that is 0.28. Probability of fixing 6 cars a day, that is 0.24. Probability of fixing 7 cars, that is 0.10. And probability of fixing 8 cars, that is equal to 0.07. Okay, so these are the probabilities provided to us. These are the probability is provided to us. Okay. What is the probability that he will serve at least 5 cars on his next day at work? At least 5 cars. That means it could be at least 5 means 5 or more than 5. Am I right? At least 5 cars means 5 and more than 5. Now see, one thing is you can find at least 5 cars means you can get probability of 5 cars, 6 cars, 7 cars, 8 cars, and you can add these numbers and you can get the answer. But other way around, at least 5 cars means if E is the event, suppose E is the event, that at least 5 cars are at least 5 cars are serviced. At least 5 cars are serviced, right? So probability of E, that is equal to 1 minus probability of E dash. Agree? At least 5 cars are serviced. That means what is the event E dash? E dash is nothing but where E dash is nothing but E dash is the event where fewer than 5 cars are serviced. Fewer than 5 cars are serviced, right? Fewer than 5 cars are serviced. So probability of E, that is natural, fewer than 5 cars means, fewer than 5 means just these 2. So it is just, you need to count just 2. So probability of, I would say that, yes, please, probability of servicing 3 cars or probability of servicing 4 cars in the bracket, don't forget bracket. So that is equal to 1 minus, this is 0.12 and 0.19, so it is 0.31. So that is equal to 0.31. So 1 minus 0.31, 0.69. So probability of fixing at least 5 cars, means 5 and more cars a day on a working day for that particular mechanic of servicing a car, that is 0.69. So there are maximum chances that he can fix 5 or more cars in a day. So actually it is something like this. So we are doing probability of E greater than or equal to 5, right? Probability of E greater than or equal to 5. And that is equal to, as I told you, that you can count this number 0.28 plus 0.24 plus 0.10 plus 0.07, and that is also 0.69. See here, but you need to count 4 points. Here we just first 2 will give the answer and subtracting. So both ways you can do like this. So because this is the complement, I solved this example using the complement of an event. Complement of an event. Right, guys? So that's how we can solve the examples. Now let's go for some of the examples from the exercise problems, and then after probably we will be completing this article, and then we will start the next article, that is the, maybe next time, that is a conditional probability, independence, and the product rule, right? That is the next article. But before that, I just would like to go over a few of the examples from your exercise problems. Okay, so first example, let me save this file in a folder, clear the drawing, stop sharing, and let me go for let me go for the book example. Okay, so now let's go for this part. Example number 2.49. Look at here, guys. Example 2.49. It says that find the errors in each of the following statements. We need to find the error. What is the error in each of the statements, right? It says that the probability that an automobile salesperson will sell 0, 1, 2, 3 cars on any given day is in the February are respectively 0.19, 0.38, 0.29 and 0.15. All these numbers are between 0 and 1, looks okay. Nothing is negative, looks okay, but some should not be more than 1. But if you count this one, 38 and 19, 57, and then 29, then 15, so that is 62, right? 62 and 29. Look at over here, 62 and 29. What can you say about this? The sum of the probability exceeds 1, right? That is 101. 62 and 20, oh, sorry, 62, 72 and 29, that is 101. So some of the probabilities exceeds 1. That means this is the wrong statement. Something is wrong in the statement. So you can say some of the probabilities exceeds 1. B part. The probabilities that will rain tomorrow is 0.40 and the probability that will not rain tomorrow is 0.52. Now rain tomorrow is event A. So its complement will not, there will not be any kind of rain tomorrow. That is event B. That means event A, that is not actually event B, that is the A complement because raining and not raining. So event and it's negative. So it's complement. That means if you add, as I just now I told you on the whiteboard that if you add event A and its complement, you have to have probability of the full space, sample space S, and that must be equal to 1. Here you can see 0.40 and 0.52. 40 and 52, that is less than 1, and that's why sum of the probabilities is less than 1. That's the error. The probability that the printer will make 0, 1, 2, 3, 4 and or more mistakes in setting the document are respectively this. You can see negative. Probability should not be less than 0. So negative number, that is the wrong thing. Negative probability is the wrong part over here. Another is on a single draw of a deck of playing cards, the probability of selecting the heart is 1/4. Heart, how many hearts are there? Probability of selecting heart, 13 hearts are there out of 52 cards. So 13 divided by 52 is 1/4. Sounds good. This is perfect. Probability of selecting a black card is 1/2. How many black cards are there? 6 spaces and blacks. So we have 13 and 13, 26 out of 52 card deck. So 26 divided by 52, 1/2. So that is also correct. And the probability that selecting both a heart and a black card is 1/8. How could it be possible? Heart means 13 cards, red color, that is just the heart, right? And the black card, once heart is red color, black card is not, there is nothing to do with the heart because there is nothing common between these two events. So both the events are separate, nothing is common. It says that heart is suppose event A and black card is event B. So A intersection and is there, A intersection B is 1/8, but nothing is common because once you choose heart, red, heart means red card, it has nothing to do with the black card, right? So both are separate. So this probability must be 0. This probability must be 0, but it says 1/8. So that's the probability of both heart and a black card is 0, not 1/8. No, 1/8. That is the answer. That should be the answer. Right, guys? Good. This way you can solve the examples. Let me go for one more example. Suppose let's go for example number what? 2.52. 2.52. I think I need to explain to you this example on the whiteboard, but first of all, just try to go through this example. It says that, suppose that in a senior college class of 500 students, it is found that 210 smokes. Now 500 students, that is my sample space. 210 smokes, 258 drink alcoholic beverages, 216 eat between meals, 122 smokes and drinks alcoholic beverages, 83 eat between meals and drink alcohol, means common part, 97 smoke and eat between meals, and 52 engage in all, means A intersection B intersection C, all three parts. Engage in all three of these bad habit practice, health practice. If the member of this senior class is selected at random, find the probability that the student A part smokes but does not drink alcoholic beverages. Student smokes but does not drink alcoholic beverages. Right, guys? Good. Then after, eats between meals and drinks alcoholic beverages but does not smoke. Smoke but does not include. See, I can say something like this. It smokes, that means I would like to use the symbol capital S, smokes. Then drink, I would like to drink alcoholic beverages. So I would like to say drink capital D for drinking, right? Then capital E for eating. That these are my three sets, and other are just in terms of intersection. Okay. My first part says that smokes but does not drink alcoholic. Smoke but means smoke and does not drink alcoholic beverages, means I would say that S intersection does not drink. Drinking means D. Does not drinking means D complement. So S intersection D complement That's what we need to find over here in A part. By B part says that it's between meals, means capital E, and drinks, alcoholic, means intersection D, but does not smoke, intersection as complement, does not means complement, as complement. So we are going to find E intersection D intersection as complement and its probability in B part. C, neither smokes nor eats between meals. Neither smokes means as complement, both simultaneously, nor eats between meals means intersection E complement. So as complement, intersection E complement. That's what we are going to find in part C. So now you have complete idea of this example 2.52. Now I would like to switch over to the whiteboard to give you the better idea and the solution of this problem. So again, let me switch over to my whiteboard. Okay, guys. So example number 2.52, right? So 2.52. Let me just draw the picture for you. Maybe it will give you a little more idea. So here it is S, here it is one portion, here it is second portion, here it is third portion. And here, as I told you, these are the number of students who smoke. These are the students who drink alcoholic beverages, D, as I told you, and these are the students who eat between meals. 210 students are there, those who smoke. Then 258 students are there, those who drink alcoholic beverages. There's nothing to do with other two events. And 210 or how many? I don't know. What was the number for E? I think 216. I forgot, but I think it was 216. Anyway, then after here it is 122 who smoke and drink alcoholic beverages. There are students 97 who smokes and eat between the meals. There are students who drink and eat between the meals, that is equal to 83. And 52 students, they are doing all these three bad habits. All these three bad habits. As I told you, my first part A that says that what? A says that smokes but does not drink alcoholic beverages. Smoke but does not drink and intersection alcoholic beverages, and I'm looking for its probability. So that is equal to, how can I find this probability? That is equal to probability of, see, whenever you want to go for S intersection D complement, just try to see this small figure. This is my S and this is my D, S and D. So D complement means all this part outside D, all this part outside D. Intersection S means this portion, common portion, intersection S. So how can I write this in the mathematical form in terms of the set theory? So I can write that is equal to, pay attention, I just want to remove this portion, this intersection portion, and this is S intersection D. S intersection D. I want to remove this portion from S. So I would say that S intersection D complement, that is equivalent to say that probability of S minus probability of S intersection D. Does it make sense? So probability of S and this one. Good. What is probability of S? We have 210 students. They are just smoking. It has nothing to do with other events. 210 out of how many total students were there? 500 students. So my S was 500. S was 500. So out of 500 students minus S intersection D, that is equal to 122 students out of 500. So whatever the numbers I'm going to get, I think that is equal to 88 if I'm not wrong. So 88 out of 500, and you can use your calculator. You're going to get the answer some 0 point something, right? 0.34, something like that. I don't know. Just use your calculator. That is the probability of the students, those who are smoking but does not take alcohol, does not drink alcohol. That is my part A. My part B. Part B says that eat between meals, means E is there. Eat between meals and drink alcohol beverages, but does not smoke. Does not smoke means S complement, but does not smoke. And we are looking for the probability of this event. So probability of this event, that is again the same thing. I would like to consider this as just one set. So if you apply the same concept, whatever the concept I applied here, if you apply the same concept, I can write probability of E intersection D, just like my S E intersection D, and minus probability of all these three, E intersection D and intersection S. So if you use the same thing in the Venn diagram like this, you're going to get the same thing. E intersection D, E and intersection D, that is this part. E intersection D is this part, right? But we need to remove this one. So E intersection D minus E intersection, just remove this part. So that is equal to E intersection D, that is given to you. What is E intersection D? E intersection, that is 83 divided by 500, and E intersection D intersection S, that is equal to 52, if I'm not wrong, right? So 52 divided by 500, so that is equal to 31 divided by 500, and whatever you are going to get, that is the probability of the events or students, those who are eating between the meals, drinking alcoholic beverages, but they don't smoke. Okay, third part. Third part says that neither smokes nor eats between the meals. Neither smokes, so as complement, neither smokes or eats, nor eats. So there is no eating. So both are not doing, and we are looking for the probability of these events. S intersection, S complement intersection, E complement. Now, guys, you can use the De Morgan's theorem over here. So A complement intersection B complement is, sorry, not A, probability of S union E and whole complement. Because see, look at here. Suppose you have, this is my S and this is my E, suppose, sorry, S and E. And S complement means everything outside of S. E complement means everything outside of E, right? So what does it mean? That means S complement means everything outside. So common part is just this one. Common part is just the outside part, right? Outside part. So the same thing can be written as S union E, that means the whole part, and its complement means again outside part. So that's why I wrote it down like this. That's the De Morgan's theorem. Okay, so S union E complement. This S union E complements can be written as, because you know that if you have, suppose, probability of A complement, so that can be written as probability of, that is equal to 1 minus probability of A event, because probability of A and A complement is 1. So you can subtract from 1. So 1 minus probability of S union E, and you know how to find the S union E, because probability of S union E, that is equal to 1 minus probability of S plus probability of E minus probability of S intersection E, and bracket complete. That is equal to 1 minus probability of S, that was 210 divided by 500. Probability of E is 216 divided by 500, and S intersection is 122 S intersection E, sorry, that is equal to 97 divided by 500. And whatever the answer you are going to get, that is your answer. That is the probability of neither smokes nor eat between meals. That's the probability. So that's how you can solve the examples, guys. Let me clear this slide and let's go for the next one. I know almost it is 45 minutes, so I'm going to go for 10 more minutes, and then after we will stop, because I don't want to start a new article just for 5-10 more minutes. So we'll stop over there. So let me go for a few more examples, couple more examples, I would say. And example 2.53, you can do it by your own, similar kind of example. So I don't want to go for this one, but I would like to go for example 2.49. So 2.59, I'm sorry, 2.59. Let me just stop sharing this one so that you can read the example before I start it. So 2.59, no, sorry, 2.59 is here. 2.59. I like this type of example. Look at over here. In the poker hand consisting of 5 cards, find the probability of holding 3 aces. How many aces are there in the deck of card? 4 aces, right? Each color. Blue, I mean to say black, red, diamond, space, right? Then 4 hearts and 1 club. 4 hearts and 1 club. So again, 3 aces. How many aces are there? 1 is club, 1 is diamond, 1 is red, 1 is black, right? 4 aces. Then 4 hearts. 4 hearts. How many hearts are there? Hearts means red color. 13 hearts are there. Out of these 13, you are looking for 4. How many clubs are there? 13 clubs are there. Out of 13, you're looking for 1. So 4 plus 1 is 5. So 5 cards are made like this. Here it says that find the probability. Just 1 minute, guys. Okay. So in a poker hand, find the probability of holding 3 aces. 3 aces, that means how many aces are there? As I told you, 4. Out of 4 aces, you are going to pick 3. That means other 2 cards can be picked up by any of the rest of the 48 cards. Right? And don't forget the total number of outcomes, please. Don't forget total number of outcomes. So here also we are going to use rule number 2.1 with the theorem, rule number 2.1 and with rule number 2.3. So this is the example of the combination of rule number 2.1 and 2.3. Read this card. I think you have read this example twice. So memorize these numbers and let's solve this example on a whiteboard. So my A part says that this is example number 2.59 and A part says that 3 aces. 3 aces. Again, 52 cards in a deck. 52 cards in a deck. How many total 4 aces are there? 4 aces, you are looking for 3. So it is collection is 4C3 because there is no restriction. You can choose any card and there is no order. You can choose red ace first and then black ace, or you can choose club, you can choose diamond ace, whatever you want. So out of 4, you need to pick 3. So total choices of 3 aces out of 4 in a 52 card is this one. Always you need to divide by how many total cards you are looking for. 5 cards from 52 card deck. So this is my event actually N1. My second event. Now I have chosen 3 aces out of 4. 3 aces. That means how many cards are left out from the 52 cards? 48 cards are left out because 4 aces I chose 3. Now 48 all other cards except aces. And I need to, how many cards I want to choose? In general, 5 cards. 3 cards already I chosen. So another 2 cards I'm going to choose from this one. So this is my event N1. This is my event N2. My rule number 2.1 says that N1 times N2. And so this is my rule number 2.1. And combinedly, I would say that it is my rule number 2.3. So rule number 2.3, that is N divided by capital N. So this is my N divided by capital N. And then use your combination problem. So that is equal to 4 factorial divided by 4 minus 3 factorial. 4 minus 3 means 1 factorial and 3 factorial times 48 factorial divided by 48 minus 2 means 46 factorial and 2 factorial divided by 52 factorial divided by 52 minus 4, that is equal to 47 factorial and 5 factorial. It's not a big number, guys. It looks like very big number, but actually it is not, because 4 can be written as 4 into 3 factorials. This 4, let me write it down over here, 4 into 3 factorial. This 3 will get cancelled out, so only 4 is left out. Okay, so that first part is done. Multiplied by 48 can be 48 factorial, that is 48 multiplied by 47 times 46 factorial. 46 factorial. This 46 factorial, this will get cancelled out. This 2 factorial is simply 2. So 2, and here it is 24. 24 multiplied by 47. So 24 multiplied by 47. Okay, and okay, and denominator is same way. 52, that is written as 52 times 51 times 50 times 49 times 48 times 47 factorial divided by 47 factorial and 5 factorial. This 47 factorial will get cancelled out. 5 factorial is 5 into 4 into 3 into 2. So if you use this one, you're going to get one number over here. Use your calculator, and that is the answer of getting 3 aces. Same way, my B part says that 4 hearts and 1 clubs. 4 hearts and 1 club. Now, how many hearts are there? As I told you, my first event, 4 hearts. Out of how many hearts? we have 13 hearts, 13 red color heart. So heart means red color always. So out of this 13, I'm going to pick 4. So 13C4, that is my combination. Already 4 cards have been chosen. How many is left out? Just 1 card is left out. But that 1 card must be club. How many clubs are there? Another, yes, please, 13 clubs are there. Out of this 13, I need to pick 1. And total number of cards I have to pick 5 from 52. So again, this is my N1 times N2, and this is my capital N. So it is the combination of rule number 2.1 and 2.3. So this way you can solve the example 2.60. This is example 2.59, 2.60. That is exactly similar to this one. So I think you can go for homework for this one. So I don't want to go for this one. I think you can solve this 2.60 by your own, because that is really, really simple. Then after, I can go for one more example, probably one more example, that is 2.61 is same as your example 2.51. So 2.61 is also homework. 2.61, that is similar to 2.51. So this 61, I think so. Let me see. Yeah, 2.52. 2.52, not 51, similar to 2.52. So you can solve this example also by your own. And let me now stop sharing this one. Let me save this one. This is in the folder, and this is page save. And now let me clear this one. Let me stop sharing this one, and let's go for probably the last example, and then we'll stop. I don't want to go beyond this point. Okay. So I think another example that is really easy. So all the examples are good. They are simple also. So I think that's more than enough. I just don't want to help you and give you a spoon feeding. So I think for fewer of the examples, I would like to leave it to you. And I think that's a good idea too. So these are the examples. Just look at over here. This is another page. So if you can take the printout, just a picture of this page, and try to go over the examples. If you don't want to buy the book, in that case, you can do like this. Or probably this book is online also. So you can do that part too. Or Amazon is the cheapest way of getting the book. I'm not advertising anybody. Anyway, but the next time we are going to start the conditional probability, independence, and the product rule. That's what we are going to start next time. So these are the things I wanted to cover today. Almost it is an hour. So let me stop over here. Thank you so much, guys. And looking forward to hearing from you next time. So next time we will be doing that article 2.6. Let me stop my recording also. The pausing.